Starting from this point, let's examine and analyze the evolving trends and developments in predictive AI research. When designing products with generative AI, it's important to understand the big picture that follows. First, X refers to the design, Y refers to performance metrics, and Z represents the latent space. For example, if there is a high-dimensional space called X, you can use a deep learning encoder to compress it into a lower dimensional latent space G, and then, by decoding it, you can restore it back to the original space. In this way, you can think of everything happening within this compressed space, E or G. So there are three things we need to look at. These are AI-based performance prediction, AI-based design generation, and AI-based optimal design. First, for example, if you have X and Y data, then Y is fx like this. Thank you. Performance prediction is possible. After that, to generate designs, you train a generative model as follows, where the output of the generative model is X, and the input is G. Here, this refers to the reduced latent space. So when you input G, X is generated, and then optimal design becomes possible. Optimal design can be done in two ways. There are two methods. One is to perform optimal design using a traditional optimizer, and the other is to use deep learning for real-time inverse design. With the traditional optimizer method, you provide a target, generate a design, and then input the generated value into the prediction model to find the G that minimizes the difference between the predicted performance and the target. Then, if you feed the G that satisfies the target performance back into the generative model, you can obtain the optimized X. And the inverse design method doesn't proceed sequentially like this. Instead, it directly gives the target Y itself as a condition to the generative model. This way, it enables the model to find the optimized X for a given Y. As I mentioned earlier, AI-based design research is optimization using the low-dimensional space G, not X. This time, let's take a look at research on AI-based performance prediction. There are various issues involved. I've gathered 4 notable issues among them for us to review. When selecting a predictive AI model, you first need to consider factors such as what the inputs and outputs are, whether time is taken into account, the level of complexity, and whether multiphysics is considered. For example, if your design is parameterized, then you can use parameters as inputs, which makes the task easier. In the diagram, the upper right represents lower difficulty, while the lower part indicates higher difficulty. For instance, there may be cases where the geometry cannot be parameterized, such as when it is represented only by a mesh or a point cloud. Also, if the output is a scalar value, the task is easier. If the output is a field value, it becomes more difficult. That's because in the case of a field value, you have to predict high-dimensional data. Also, if the situation is static, it's easier since you're predicting a single time point, but if it's dynamic and you have to consider all time steps, it's more difficult. And if what you're trying to predict is a single part, a single component, then it would be a bit easier. But if it's an assembly, then it gets more complicated. And if the data I'm trying to train on is single fidelity, for example, if it's KAIST data or test data, then it would be easier. But if you have to train both the CA data and the test data together, then you need to consider multi-fidelity. With this background knowledge, the issues we're going to address are dimensionality reduction and field prediction. First, let's look at training a predictive model using dimensionality reduction. Traditionally, when there is a design space X and a response or performance space Y, we have built predictive models that go directly from X to Y. However, this approach does not work well when both X and Y are high-dimensional. So what we do is if X is high-dimensional data, we first perform dimensionality reduction from X to obtain Z. After reducing the dimensionality to Z, we then move from Z to Y. It's like a pathfinding problem, not going directly from X to Y, but first reducing X to Z and then going from Z to Y. Or, if Y is, say, 5-dimensional, you can reduce Y to W, then go from X to W, and from W to Y, making prediction possible. Alternatively, the reduced design space and reduced response space can also be connected in this way. It could even be done in 3 stages. Since various combinations are possible, you should utilize the prediction model according to the state of your data, as shown here. And there are also advantages when you perform dimensionality reduction. You can combine dimensionality reduction and prediction as follows. For example, let's say you have a material. If you perform dimensionality reduction on the image of the material like this, and then restore it, the image will be reconstructed. In this case, the reduced space extracts the important features that can best reconstruct the image. However, the problem in engineering design is that these features shouldn't just be for simply reconstructing the image, but rather they need to be features that can effectively capture the engineering performance. So how can we extract features that are related to engineering performance? The first method is to attach a regressor to the reduced space, like this. So not only do we reconstruct this, but we also train the latent space so that it can predict some engineering performance at the same time. By doing this, the latent space comes to understand the shape well, while also gaining a good understanding of the engineering performance. And there's another method. This was the first method. The second method is a way to overcome the lack of data. Earlier, I mentioned X and Y, and for example, there are often cases where there is a lot of X but not much Y. When there aren't many label values, if you first reduce the dimensionality of X as shown here, and then attach a regressor in that reduced dimensional space to make predictions, the predictions tend to be more accurate. So there are two ways to connect prediction and dimensionality reduction. And if you look at various cases where predictions are made using dimensionality reduction like this, first, here's a case where the stress field was predicted. In this study, for example, the shape of the beam was visualized as an image. The forces applied in the X and Y directions were also represented as images, and the boundary conditions were included as well. After representing which parts need to be fixed as images, those are used as inputs. Dimensionality reduction is performed, and then the reduced dimensions are restored so that the stress field values can be obtained. In research, how should I represent the design problem I have? There are various methodologies for this. Next is a case where the flow field was predicted. Thank you for this part. As you will learn later with this airfoil, instead of using a simple image, it is converted into what is called a signed distance function and then used as input. It's a type of distance function. It's a distance equation. Anyway, you input this value, perform dimensionality reduction first, and then in the reduced space, you add your design variables or environmental variables like Mach number or Reynolds number, and then reconstruct it. When you reconstruct it, you train the model so that the restored value becomes the flow field value you want. This time, it's a case of predicting the temperature field. Depending on the location of the heat source in the temperature field, you check how the temperature is distributed. So, as you can see, the heat source becomes the input and the temperature field becomes the output. When you do it this way, you predict by first reducing the dimensionality and then restoring it, as shown here. So, instead of directly predicting y at fx from here to here, the reason for reducing the dimensionality first is that by doing so, the prediction is made based on the important features. This approach leads to better predictions. And in this case, what's interesting about this study is how it performs data augmentation. Instead of training on X and Y directly, it uses the differences between the X values you have and the differences between the Y values you have, which creates a wide variety of combinations. It trains on those difference values. So when you input the difference values, the model is trained to predict those difference values. This is an example of an idea that uses data augmentation in this way.